Oh, sorry, Yash. You can also use this.
Oh, yes. Consisting of piecewise linear homeomorphisms such that the following holds. So one, the slopes, whenever defined, are integral powers of 2 . And second, the breakpoints where slopes are not defined there must be finitely many for each element. Lie in the dyadic rationals. Okay. So one can construct lots of such piecewise linear homeomorphisms. Let me give you a couple of explicit examples. So I'm going to consider right actions unless I specify that it is a left action. In the case I need to use function notation. So I'm going to define a homeomorphism x naught acting on a point t in the unit interval as follows. So this is 2t if t is in the interval 0, 1/4. It's t plus 1/4 if t is in 1/4, 1/2. And t plus 1/2 if t lies in 1/2, 1. Okay. So now essentially what I'm going to do is that so you can check, by the way, that this satisfies the definition. So this element has the property that it is piecewise linear. Slopes, whenever defined, are integer powers of 2. And the breakpoints, which are these points, are dyadic rationals. So essentially what I'm going to do is I'm going to take the unit interval, and I take the right half, which is this guy here. I just blow it up, just scale it, rescale it by a factor of 2, apply this element, and then conjugate back. And I'm going to get this new element, and then I have the identity on the left-hand side. So I'm going to get this new element, x1, which is going to be t if t is in 0, 1/2, 2t minus half if t lies in 1/2, 5/8, t plus 1/8 if t lies in 5/8, 3/4, and t plus 1/2 if t is in 3/4, 1. Now, remarkably,
sorry, Yash.
Yeah.
This is x naught conjugated by what?
So this is a piecewise linear homeomorphism of 0, 1. And if you sort of restrict yourself to this, right? I mean, if you restrict x1 to just the right half of the unit interval, then the shape of the homeomorphism is exactly this. So this is just a topological conjugate of this homeomorphism of the unit interval to the right half of the unit interval. I'll make that precise in a moment. So remarkably, the group F is generated by x0 and x1. This is not at all obvious, that this is the case, but you can make an abstract definition and you can construct elements, but it's not at all obvious that this group is finitely generated, even two generated. So this is sort of how Thomson discovered. Well, Thomson discovered the group in the context of the logic of associative of the associative operation, but this is sort of the first avatar of the group that emerged in his writing, and now this is a very specific sort of object, right? I mean, it seems like it emerges in sort of a very specific way, but in fact that's not the case. In some sense, the group F is ubiquitous in the group of homeomorphisms of the real line. And so let me state a lemma, which I like to call the two-chain lemma. So I'm going to draw a picture, and that picture will encode a certain group action. So this is the real line. I'm going to fix 4 points. This point I will call x, and this one y. And I'm going to draw this arc, label this by f and this by g. So f and g are orientation-preserving homeomorphisms of the real line, satisfying the following dynamical hypothesis. So f fixes everything to the left of this point, pointwise, and everything to the right of this point, pointwise. And in the open interval here, f moves points away from this point and towards y, right? So this is like a sort of a dynamical orbital diagram. It doesn't tell you exactly what f is. It just tells you sort of the shape of f. And the same with g. G fixes everything to the left of x, everything to the right of this point. And in between these 2 points, g moves points away from x and towards this point, right? That's all I know. Now, the lemma states the following. If the point x, when hit by f, followed by g, the image is at least y, then the group generated by f and g is isomorphic to Thomson's group F. Okay? So remember, I didn't specify precisely what these homeomorphisms are. I only told you what they look like in this sense. And as long as they satisfy this dynamical hypothesis, the group they generate is going to be isomorphic to that group, which is sort of a very special, piecewise linear group. Moreover, the group F is finitely presentable. So Thomson proved that F is finitely presentable so it admits a very natural and beautiful presentation. So x0 and x1 are those two generators, and the relations are the following. So I have x0, x1 inverse commutes with x1 conjugated by x0, and so here, notation, bracket AB is the commutator of A and B. So this is A inverse, B inverse, AB. And A raised to the B is B inverse AB. It's the conjugate. Right? So these two relations are satisfied by these two. You can actually check them by hand. And now there is a fact about Thomson's group F that every proper quotient of F is abelian. Okay, so we'll come back to this fact in a moment, but I just want to isolate it at the moment. So this guy over here, if I take f times g, comma g, so if I call x naught f times g, and my x1 is simply g, then you can check that because of this hypothesis, these two relations will be satisfied. Okay? And because every proper quotient of f is abelian, and since the relations hold, we know that this must be a quotient of f. And since this is clearly not abelian, right? I mean, these two homeomorphisms don't commute. This is isomorphic to f. And so now a useful corollary is you can choose these homeomorphisms to be smooth. Right? You can, C infinity. You can choose them to be C infinity diffeomorphisms. And so this gives you an action of f by C infinity diffeomorphisms on the real line. Okay? And that action is very much not C infinity. In fact, it's not C1. Now, this is where sort of yes?
So what's the relation between x0 and x1 as you define them here, and the x0 and x1
Right, so so this is my group generated by fg. If I construct an element which I call x0, which is simply fg, and an element x1, which is simply g, then these two are now words in this generating set, and they will satisfy the same relations as those guys.
And what's the relation with the x0 and x1 that you defined explicitly before?
So that's the generating set for the standard action of f, right? But this is just some abstract action, right? I mean, this action may have nothing to do with that a priori. It'll turn out that in fact these two actions are semi-conjugate to each other. But the point is that because every proper quotient of f is abelian, if you have two elements of your group that generate the group and satisfy those relations, then that means that that group must be a quotient of Thompson's group f, right? But since every proper quotient of f is abelian, and this is non-abelian, this has to be on the nose Thompson's group f, right? So now we come to the piecewise projective picture, which is really the title of this mini course. Recall that PSL2R, which is the group of 2 by 2 matrices with real entries and determinant 1, acts on the circle, which I identify with the reals together with a point at infinity. So this is just the real projective line, and topologize it as such. This action is given by fractional linear transformations. So if I have a matrix in PSL2R acting on a point, so we have to be a little bit careful. So let me just So now this is going to be ax plus b divided by cx plus d whenever defined. Okay, so this fraction may not be defined because the denominator may be infinity. And infinity, maybe 0, and infinity otherwise. Okay, and here x is in R. And the convention is that A, B, C, D acting on the point infinity is simply A over C. So this is the so-called action by projective transformations or Mobius transformations. And the idea is to build piecewise projective groups So if I take a copy of the real line and slice it into finitely many intervals, let's say I1 through In, so I1, the left endpoint of I1 will be minus infinity and the right endpoint of In will be infinity. And I define a homeomorphism F such that the restriction of F to each ij agrees with the restriction of G, or let me give this an index as well, Gj to ij for G1 through Gn in PSL2R. Okay, this is what I call a piecewise projective homeomorphism. So it's a homeomorphism of the real line, orientation preserving, for which there exists a finite partition of the real line into intervals, such that the restriction to each interval coincides with the restriction to that interval of some projective homeomorphism. Okay? It's just like piecewise linear, except with projective pieces. So now, the remarkable observation of Thurston was the following. F is isomorphic to the group of piecewise PSL to Z projective homeomorphisms of R with breakpoints in the rationals. Right, so remember when I defined piecewise projective, I said we have a partition into intervals and so that the restrictions coincide with some Gj. Now, the breakpoints are these points where we glue together these intervals, and I require that a breakpoint is a real breakpoint, so it has, you know, the restriction to its left and right come from different projective elements. Okay?
Did you mean to say definition here?
Definition, yes. This is kind of a theorem definition. You know, this is another equivalent, you know. So yeah, I guess I'll just say theorem.
I was confused because you said it's a remarkable.
That's the thing. It's an interesting philosophical question. Like, is this the? I mean, some might argue this is the right definition of Thomson's group, right? In a sense, yeah, this is so. Thurston observed that this group is isomorphic to the group that I've been discussing. Yes. Yes, absolutely. So you can construct piecewise projective homeomorphisms of the circle, and you know, people study these groups, and there's lots of examples with interesting properties. You can get simple groups like that. This group will not be simple, but you can get finitely presented in simple groups like that. So I'll talk about that more later in the course. Yes. Sorry?
Can you also formulate Thompson's group?
Yes, absolutely. So if you replace, as you pointed out, so if you replace R by S1 by the projective line and make the same definition, then that's Thompson's group T. Yeah.
What about V?
V no. Well, V you can V doesn't act continuous map. So you can formalize it in this way that you have piecewise projective allowing finitely many discontinuity points, and the restriction to each interval agrees with some projective map, and that's V. So if you formalize it a little bit differently, you get V. Yeah. Okay. So what I'm going to do is I'm going to so this is sort of just the big picture. I'm going to go back a little bit to the original definition, which was the group of piecewise linear homeomorphisms at the top. And I'm going to give you another interpretation of that. So I'm going to give you a way of describing elements. Of F combinatorially. So a dyadic interval J subset of the unit interval is of the form, so this is a definition. For some n please 0 and I between 0 and 2 to the n. A partition J1 through Jn of I is called regular if 1, each Ji is a dyadic interval, and 2, so this is in order, so sup Ji equals inf Ji plus 1. Okay. So there is a very natural way of building dyadic partitions of the interval. By using finite rooted binary trees. So this is my unit interval. Okay. This is a dyadic partition. Another thing I could do is I could slice it in the middle. And what this corresponds to is I start with a rooted tree with no edges. That corresponds to the original dyadic partition. And then I add a caret with 2 new leaves. And this corresponds to this subdivision. Okay? Now I may choose to subdivide this interval or this interval, and I add the corresponding caret. So let's say that I do this and I subdivide this, okay? And maybe I do this and I subdivide this, and I keep going, right? So for every finite rooted binary tree, I have a corresponding dyadic homeomorphisms of the Cantor space, which can be viewed as the boundary of the infinite rooted binary tree. And these are sort of prefix replacement maps that give you those homeomorphisms. But these things don't act on the tree itself. So Gregorchuk's groups and self-similar groups, they act on the tree, right? They permute things around and they preserve the edge relation. These maps don't preserve the edge relation. They preserve the edge relation up to finitely many edges. So there's an error. However, they do act faithfully on the boundary of the infinite rooted binary tree. So I'm going to come to that in a moment. I'll come to the boundary action in a moment.
Sophic approximations to Gregorchuk group?
Sorry?
What you said makes it sound like there's Sophic approximations.
No. In some sense, these groups, like algebraically, they're completely different from Gregorchuk's group. They really have nothing in common. I mean, here you have exponential growth. You have this quite likely non-amenable. It's a very different landscape of groups. Where the similarity comes in is that you have a nice action on the Cantor space that encodes a lot of interesting properties. So there's an analogy rather. But one interesting line of research that people have seen a lot of success with is that you take this action or an action of one of these generalized Thompson groups on the boundary of the infinite rooted binary tree, and you take your favorite branch group, maybe Gregorchuk's group or maybe some other group, and generate a group that acts on the boundary of the infinite rooted binary tree. These are called the so-called Rover-Nekrashevich groups, and these have really surprising properties. And so that's a so yeah, there is something in common, but at least like for now they're completely different objects. So here's another remarkable property of Thompson's group F. A group G satisfies a law if there is a non-identity element W in some free group Fs, which is freely generated by S, some set, on some finite set, such that every homomorphism from Fs to the group G, such that for every homomorphism, W lies in the kernel. Okay? So the way you should think of, the first example you should think of is abelian groups satisfy the following law. So if I take the free group of rank 2, freely generated by A and B, and I take the commutator of A and B, then for any homomorphism from the free group to your abelian group, this will vanish, right? And so abelian groups satisfy this law. And if a group satisfies a law, then it cannot contain a non-abelian free subgroup, right? And if a group, contrapositively, if a group contains a non-abelian free subgroup, it does not satisfy a law. Now, this raises an interesting question, which was sort of a classical question. Can you have a group that does not satisfy a law, yet does not contain a non-abelian free subgroup. So the reason for it to not satisfy a law doesn't come from the fact that there is some subgroup which is a free group, which is kind of a very sort of naive reason for it to not satisfy a law. And it turns out that Thompson's group F answers this question. So this is a theorem of Brin and Squire from 1984. F does not contain the free group of rank 2, yet it does not satisfy a law. Okay. So I want to give you a sketch of a proof of this. I don't have enough time to give you all the proofs in this mini course, but I want you to have a sense of how the proofs go and sort of come back with a sort of a set of techniques that maybe you will use in your research. So let's focus a bit on the part that it does not satisfy a law. Now, the original proof of that is a little bit more complicated. There's many different ways of proving this, but the one that I like the most is of the following criterion due to Miklós-Hebert, which you can also apply in other situations, right? So it's a nice, simple criterion. So I have a group G acting on a set X by bijections, okay? G is said to separate X if the following holds. If for all Y subset of X finite, the pointwise stabilizer of Y in G, so this is the set of elements in G which fix every point in Y. This is a subgroup. Does not fix a point in the complement, so X minus Y. So if I take a finite set Y in X, then the set of elements that fix that set pointwise, it's a subgroup, will move every point in the complement. So for every point in the complement, I can find some element of the subgroup that moves that point, right? So the theorem of Hebert is that such a G does not satisfy a law. So you can check this. You can check this criterion for the action of F on the open unit interval or just on the dyadic rationals. And you can just build elements. Like if take your favorite finite tuple and some other point that doesn't lie in that finite tuple and construct an element that fixes those points but moves the point that you chose at the end. And this can be done very easily. Just take a small neighborhood around that new point and build something that only acts locally there. That's the proof. The proof of Hebert's criterion is also very easy. It's one of those cute things that maybe to come up with was complicated, but once you know the statement, proving it is really a homework exercise. You should go back home and think about it, and I'm sure you can do it. So it's like when I saw the proof of non-sophisticity by the OpenAI, the announcement last weekend. Once you know the statement of that proposition, then and you have some understanding of the area, then you can fill in the details. But isolating the statement was remarkable. Okay, so this is the proof that F does not contain does not satisfy a law. How about the proof that F does not contain a free group of rank 2? So let me give you a sketch. So the way to think about this kind of question is by means of these diagrams called orbital diagrams. So if H is a subgroup of the group of orientation preserving homeomorphisms of some one manifold, like let's say the real line, could be an interval, then an orbital of H is a connected component of the support of H. So the support of H is the open set consisting of points that are moved by some element of H. So there is some little h such that x dot little h is not equal to x. This is going to be an open set, and so it's going to be some union of intervals, and if you pick your favorite connected component, that's an orbital. And similarly, we can define orbitals of elements. So orbitals of elements are simply the orbitals of the subgroup they generate. Okay. And so now what you can do is you can draw a diagram. So let's say that I have an element F, and F fixes this point and then this point, and then in between these 2 points, it acts in this way. So it moves points away from this one and towards this one. And then maybe it pointwise fixes an interval. Okay, so maybe it pointwise fixes this interval. And then maybe it does this here. Okay. And maybe it does this here, and then maybe it pointwise fixes everything else here and here. So this is an orbital diagram. Okay. So now what we're going to do is we're going to assume. Remember, we want to prove this theorem. We want to prove that F does not contain a non-abelian free subgroup. We assume by way of contradiction that it does. So I have 2 elements in F which generate F2, and I draw their orbital diagrams. Okay, and then I want to do some sort of commutator tricks. Okay, so how do I do that? So let's do a simple manifestation of that, and then we can sort of convince ourselves that we can do more. So let's just take the following picture. So I have this here, and then I have this, let's say. Okay, so this is F, this is G. Okay. Can these two generate a non-abelian free group? what if I take a conjugate of G by a very large power of F? I get something that looks like this, okay? So this is a conjugate of G by F to the N. And then I conjugate F by a large power of G. So this is G to the M. And that looks like this, okay? Now this guy and this guy have disjoint supports, right? They're non-trivial homeomorphisms that have disjoint supports, and so they commute, right? And you cannot have a copy of Z square inside a free group of rank 2. So this doesn't generate a... So we want to reduce to a picture like this. But we can run into a problem. So for example, we could have a picture where something like this happens. So this is my F, and then my G looks like this, right? So now I can't do that anymore because here I'm sort of stuck, right? However, the group of germs here, remember these are linear maps, right? So the group of germs at fixed points are abelian, right? Because they're just slopes, the powers of 2, right? They commute with each other. So if I take a commutator of F and G, then this right germ vanishes. And so I get a new element which has a slightly better configuration with respect to the original F and G. And then I sort of iterate this process, and I sort of, I sort of count the number of orbitals that are sort of overlapping with each other, and then I sort of keep performing this process until I get fewer and fewer components, and then I run a trick like this. So it's a combination of these kinds of tricks that gives you the proof. Okay, so this is a really cute theorem of Brennan Squire, and it sort of illustrates why F is so special. Another important historical theorem about Thompson's group F is the Brown-Gagan theorem. This is from 1985. The group F is of type F infinity, which means that it admits an Eilenberg-MacLane complex with finitely many cells in each dimension. So type F infinity is a topological strengthening of the property of being finitely presentable. So if you have a finitely presented group, let's say that you have a group with generators S1 through Sn and relations R1 through Rm, then you can build a connected two-dimensional CW complex whose fundamental group is your group. So you start with a 0 cell and you attach loops corresponding to these SIs, so S1 through Sn. And then for each relation, you take a disk whose boundary is a word that's labeled by your relation, and attach the boundary along these letters that you read. So if, for instance, this is S1, S2 inverse, then you S1 and then S2 inverse, and so on. So you effectively null homotoping that word. And what you get in the end is the so-called Cayley-2 complex. So this is a connected two-dimensional CW complex whose fundamental group is this group. However, it might have non-trivial pi2. So what you do is you add three-dimensional cells to kill the pi2, but it might have non-trivial pi3. You add four-dimensional cells to kill the pi3, and so on. You keep going. You take the union of all of this, and you get in the end an aspherical connected CW complex whose fundamental group is still your original group. This is called an Eilenberg-MacLane complex, or a KG1, where G is your group. And the universal cover of this is contractible, since the complex is aspherical. And the group acts nicely on the universal cover by deck transformations. So this is a nice model for your group. And a group is of type F infinity if it admits an Eilenberg-MacLane complex with finitely many cells in each dimension. So the word admits here, you know, this process is highly non-unique. There's many different ways I can build this thing. However, this is unique up to homotopy type. And so admits is not such a strong, you know, it's sort of up to homotopy type. You have a complex with finitely many cells in each dimension. And the reason why this is surprising is because F was the first example of a type F infinity torsion-free group with infinite cohomological and geometric dimension. Infinite dimension. So the combination of these three properties was at the time highly, highly surprising. Of course, now we have lots of examples. There's some water below the wire. Please be careful. Of course, now we have lots and lots of cousins of this group that have this combination of properties, but this was sort of the first example. And you know, one of the many things for which this is known for, so I think I only have like 3 minutes left. So maybe I will quickly state a proposition and then continue the next time. Yeah. So for F in the group, I define chi naught of F to be the log base 2 of the right derivative at 0 and chi 1 of F to be log base 2 of the left derivative at 1. These guys are going to be homomorphisms. So these separately and together as a pair. So these separately are homomorphisms from the group to Z. And as a pair, they give you a homomorphism to Z square, also surjective. And if I call this homomorphism phi, then the kernel of phi is the derived subgroup of F, or the commutator subgroup. Okay? This is very easy to check. And the key proposition here is that f prime is simple. And each proper quotient is abelian. So the group F itself is not simple, but its derived subgroup is simple. And every normal subgroup of F contains as a subgroup the derived subgroup. So the normal subgroup structure is rather uncomplicated. And this sorry? Of F, yes, sorry, of F is abelian, yeah. And so this tells you that the normal subgroup structure is rather uncomplicated, and so the proof of simplicity of this is sort of, there is sort of we talked about simplicity of the group of where is Sam? Yes, the piecewise linear group of the circle orientation preserving and so on, and there is a very cute simplicity criterion due to Higman, which I will describe in my next lecture, and so yeah, so I'll wrap up with F in the first 10 minutes of my next lecture, and then I will move on to piecewise projective groups. Yeah. So. Yes.
Questions?
Yes. Yes.
So PSL2Z itself has a action on the complex plane, upper half plane.
Yes.
Very important for people like me.
Yes.
And question is, how about this fractional, piecewise fractional?
So you want to build some sort of piecewise PSL2Z action on the complex plane? I think that might not work because of the singularities being, because of, you can't glue maps that are analytic, right?
I see the difficulty.
Yeah.
It has not been studied. No?
Right, it hasn't been studied, yeah.
Maybe one comment. One can talk about piecewise projective homeomorphism of this sphere S2.
Yeah.
Yes.
Or piecewise
Piecewise projective, that it means PSL2Z. It's not related to PSL2Z.
I think you can restrict subgroups of PSL2R. It could be PSL2Z too. Yeah.
Right. Well, so I'll see you guys in the next talk.